Okay, hi and welcome back. This is the second of my sequence of videos on electron arrangement, and after explaining the arrangement of electrons in atoms and how they fill, then we probably want to know the evidence for that. The evidence for the arrangement of electrons principally comes from what we call the ionization energy. The graph figure you see in front of you there is very, very important indeed. We have a definite graph, we have a definite shape, we have a repeating pattern. This is a periodic function. It follows the periodic table exactly. And of course, it does generally go up as we go from left to right. There are a couple of highs and a couple of lower points, but the arrangement is something you must know full well. And in the lab, we will have, I'm sure used to have anyway, a stack of shot glasses which actually reflect this exact picture. So the graph shape is important, and your ability to explain the shape is very important too. So more about the graph when we decide what it is and how we got there and what we use it for. So what is ionization energy? The ionization energy is essentially the energy required when it comes to removing electrons. The first ionization energy, here's the definition: the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous positive ions. You frequently get asked to represent an ionization energy equation. As you can see underneath, I've used the fictitious element M, and notice I have a 1 mole of M and it must be gaseous. All ionization energies must be gaseous. So M gas, 1 mole of it, goes to M1 plus gas with the loss of a mole of electrons. So that is essentially what we're doing. We need to put energy in to knock the electron off the atom to create a positive ion. Now, how easy or how difficult that is depends on the electron structure and how readily the atom can lose an electron, or maybe it doesn't want to lose electrons. It might have a full outer shell like a noble gas and be rather reluctant to part with electrons. It might be a group 1 element that would much rather get rid of an outer electron, or a group 7 element that would desperately like to get another one. So this ionization value is just an energy measurement, and we measure it in a mass spectrometer. Don't worry about that, but we do. So the ionization energy data will reveal some very important patterns and ability to arrange electrons, just like you'll see. So we're going to show you ionization in an animation for the element carbon. Nice and simple. You're going to see this arrangement and this animation again in another video. So here comes our carbon atom, and I've built it very simply just so you can recognize it, with a nucleus containing 6 protons and of course 6 neutrons, mass number 12. And as you can see, there are 6 red electrons, and there are 2 in the closest electron shell, shell 1, and then we've got another 4 which inhabit shell 2. Well, now we would arrange them 1s2 in shell 1, 2s2 and 2p2. So we would subsection the electrons in the second shell into 2 subshells, the s subshell and 2 electrons occupying a p subshell. Well, that's not true, is it? Well, it is, but it's 2 separate orbitals in a p subshell, what I mean to say. So effectively, a nice simplified picture, and what we're going to do is we're going to take aim at our atom and we're going to fire high energy electrons at it. And you're going to see when we shoot it, we're going to knock an electron, and which one's going to go? There it goes. So when we fire electrons at our atom, then we're able to knock an electron from the outer shell, and the energy graph is displayed, as you can see, as a bar chart. 1087 kilojoules per mole was what it required to remove that 1 electron, as you can see, carbon gas to carbon 1 plus gas plus an electron. When we do that for every single one of our batch of elements, let's say up to calcium, if you will, then we will get a value for the first ionization energies. And when we do get them, this is the table. Now, of course, just so you can pick it out, I've highlighted carbon in red. That was our 1087. Well, as you can see, it's just a column of numbers, isn't it? But if you look more carefully within that column, there are some really important differences and changes. First of all, can you spot the highest value of them all? Well, it wouldn't take you very long. And of course, that's helium, 2,372 kilojoules, much more than carbon. And of course, the lowest value in the whole table, yeah, you find it right near the bottom, is of course potassium at 419, considerably lower than that for carbon. So the size of this ionization energy value reflects, if you like, the stability of the electron arrangement. The lower the value reflects the instability of the electron arrangement. The second highest value, if you look carefully, is neon, which unsurprisingly is also a noble gas arrangement in our arrangement of electrons after helium. Well, so what we're going to do is we're going to display this chart, these data values, alongside the atomic number on the horizontal axis. So when we do that, we get this. And as the bars you can see are shaded in, then what I've done is I've picked out the atomic numbers across the bottom axis, the x-axis, and as you can see, we've gone from hydrogen all the way to calcium, number 20, and the bars represent the ionization, first ionization energy for each of the elements. We picked out helium was the highest value, remember, and then neon was the second highest value, as you can see, and potassium we picked out was the lowest value. Well, within our bars and within our numbers, you can clearly see some obvious repeating patterns. These are known as periodic functions or periodicity. First of all, if you look at the yellow bars, then that takes us from the sequence lithium across to neon. Now that is the arrangement. These are the electrons, of course, in period 2. We have 2s, which is lithium and beryllium, and then the 2p, which is boron, carbon, nitrogen, oxygen, fluorine, neon. So the pattern we see there is this broadly increasing of ionization values as we go across. So broadly speaking, it gets more difficult to remove the outer electron. There are some high points and some low points. Well, they are also very significant, as you'll see. Well, unsurprisingly for the periodic table, the next time we get that exact repeating pattern is for the sequence sodium to argon. And if you're very careful, you can see that, for example, at boron, we had a little dip in the pattern. The same dip in the pattern occurs at aluminium. So something important changes in the electron arrangement after the first 2 electrons have been added. We get a slight dip at the group 3 element, boron or aluminium. We then get a slightly higher point at nitrogen in the yellow bars, and that recurs again with phosphorus. There's something special about the nitrogen and phosphorus arrangement where we've got 3p electrons have been added to the 3 separate p orbitals. There's a slight dip again at oxygen, which reoccurs ever so slightly at sulfur, but we've got a slightly less stable arrangement. Something happens at oxygen. You may recollect from our first video, we called this spin pairing, and it occurred when we entered a 4th p electron, where we now, having obeyed Hund's rule and did single occupancy for the 3 p orbitals, we now have no choice but to pair up, and that destabilizes the arrangement, so we need slightly less energy to remove the electron. And then, of course, fluorine mirrors the same position as you got with chlorine, and then we got to a noble gas again. So that pattern, we'll take that pattern and look at it in some more detail because we need to understand what the highs and lows are telling us. Second pattern within this table is to look at what happens as we go down a group. So if we take a look at certain groups, then we can see a pattern here as well. Now I've oranged up the group which is known as the noble gases, group 0. As you can see, helium was the highest of all the values for ionization 1. Then we got neon, and as you can see, the next high point is argon. Unsurprisingly, a very obvious pattern, a decrease as we go down a group. Again, you may remember this is because our atoms, the electrons in equivalent shells and subshells, are getting further from the nucleus. They're getting shielded by full inner electron shells. So more about that as well when we look in greater detail. Just pick out the green bars. This shows you group 1 elements, lithium, then down slightly to sodium and down slightly again to potassium. So the pattern, the trend going down any column or group in a periodic table is that the ionization energy decreases. So we've seen two patterns, increasing across a period and decreasing down a group. We will have to explain why, and we will. So here is the same graph, and I've picked out the important part we've got here. Again, the same pattern, but this time not as bars, but as a continuous line graph with the points plotted. I've drawn a dotted line through group 1, lithium, and of course through the next element, which of course we go lithium, beryllium, boron, carbon. And then if we carry on with our dotted line, the next one we come across is the solid line position for fluorine. So if we draw a dotted line from group 1 through to group 4, through to group 7, that's lithium, carbon, fluorine, and draw the black dotted line, then that shows us the general increase. If we repeat that for period 3, we start with sodium and then we put our line through, and of course we'll get a very similar pattern and a similar arrangement. We get high points and low points which occur in the same sort of places. So first of all, let's have a little look at the first of the sequences. That's the lithium through to neon sequence, and we're going to focus on that one, and we're going to explore the little highs and lows of that particular sequence. Here it is. So again, there's the dotted line connecting lithium, carbon and fluorine, and they are all in a nice straight line. So why do we have a little high point at beryllium and a little low point at boron? Why does the curve slightly increase at nitrogen but then dip slightly lower at oxygen? And of course, fairly simply, boron, its position, its ionization energy is below that of the elements on either side, beryllium and carbon. Nitrogen's ionization energy is bigger, higher than the elements either side of it, carbon and oxygen. So there's something special about the beryllium arrangement because it's higher than the lithium and the boron. There's something special about the nitrogen arrangement because it's higher than the others either side. And of course, neon, well, that's highest of all in this particular sequence. The low points, we have a low point at boron, which is lower than the elements either side. So there's something destabilizing and unhappy about the boron electron arrangement, and something else similarly with oxygen. Well, of course, this gives evidence and weight to our understanding of how our electron shells are filled. When we consider this electron shell, of course, this is shell 2, we first of all add the s subshell electrons, that's lithium and then beryllium. So why is the beryllium arrangement so special? Because we've got a full s subshell, spin paired but full. And then the next electron, S2p1, would be boron. So why is that slightly unstable? Well, the 2p1, the first electron, is further from the nucleus. Remember the electron in Box's picture, it's slightly further out. It's also shielded by the full 2s subshell that's in the same electron shell or energy level. So this idea of a shell shielding an outer one is that reduces the ionization, whereas a full shell increases the ionization. So basically, if we get a higher than expected value, then we've got a more stable electron arrangement. A lower than expected value, then we've got a less stable electron arrangement. So next of our high points was nitrogen. And this, of course, is familiar to us because at that point, we've got 1s2, 2s2, 2p3, three separate electrons in three separate 2p orbitals with no spin pairing. No wonder the nitrogen arrangement is very stable and therefore more energy is needed to break into it. Whereas oxygen, as you can probably gather, has now got to pair up an electron in the 2p subshell. We called it spin pairing, and it brings about repulsion between the electrons within the orbital, and so that destabilizes the electron structure somewhat. And the oxygen is therefore a low point on our graph. So it's very important that we can explain, and you will have to explain, those particular high and low points within the ionization energy 1 graph, and the high and low points are explained by the arrangement of electrons that we now know is the correct arrangement. And of course, if we didn't have the S and P subshells and the Hund's rule in terms of occupancy, then this wouldn't make any sense. We've filled the first S subshell and that gives us a stable position. We then start the P subshell and get a stable position when it's half full with 3 electrons. We get an unstable position when there's spin pairing with a 4th electron. We get another high point when we've completely filled the P subshell with all 6 electrons, and of course that is a full S and P subshell, which of course will be neon structure. So our first ionization energy gives us clear information about the arrangement of electrons in shells and subshells and orbitals. So there are, and you really realize by now, I'm just pulling this together, there are some quite clear factors that affect our ionization energy. Remember, this was the amount of energy needed to remove an outer electron. So there are effectively 3 contributing factors. And when you write about an explanation or you're asked to explain an ionization energy pattern or trend, these 3 features must enter into your answer. So you must mention nuclear attraction, you must mention electron shielding, and you must mention the atomic radius or the size of your atom, because all 3 factors come together to affect the ionization energy. So let's look at them. First of all, the nuclear attraction. This is very simply the number of protons in the nucleus. As your atom gets bigger, you get more protons in the nucleus. So as you would expect, this increases directly in line with atomic number because that is the number of protons. So the element with the higher atomic number will have greater nuclear attraction. Now there is an opposing force which pushes the electrons away from the nucleus. These is due to the electron shells, the full inner shells, which exert a repulsive force, pushing the incoming electrons or the outer electrons away. And this opposes the nuclear attraction. So quite often, when we talk about nuclear attraction, we must immediately follow up with the electron shielding, because these 2 features generally will oppose each other or counteract each other or outweigh each other, which is a useful examination question answer. Outweigh it, is to negate it, to cancel it out, to oppose it. The third feature is the feature of size. A very simple physical change. As the atoms get bigger, the outer electrons get further from their attracting nucleus. So bigger atoms attract electrons less strongly, even though they've got more protons and more shielding. The physical distance, the separation between, means that the electron can't be held as strongly in bigger atoms as in smaller ones. So when we discuss ionization energy patterns and trends, these are the three players that we must refer to in our explanation: nuclear attraction, or number of protons; the electron shielding, number of full inner shells; and the size or radius of an atom, which is a measure of the distance, if you like, from the nucleus to the outer shell, which is generally a size increase as an atom obviously gets an increased atomic number. There are some patterns within these things, and we'll look at those. So here is our simple illustration where we've combined all three features, and we're going to look at the effect these have on the ionization energy, the amount of energy we need to put in to pull out that outer electron. The nuclear attraction pulls the electron in, the electron shielding pushes the electron out, so they sort of balance each other, and the radius, the atomic radius, is a physical measure of how far the electron is from the nucleus. Further away it is, the less strongly it's attracted. So fairly obviously, when we deal with our three features, nuclear attraction, as the nuclear protons get stronger, then the attraction for the electron increases. As the amount of shielding from full inner shells increases, so the repulsion for that outer electron increases as well. So nuclear attraction is often accompanied by increased electron shielding. Bigger nuclear protons also come with bigger numbers of electrons and bigger atoms. And then, of course, the third component is our atomic radius, the physical distance from nucleus to outer shell. And again, as our atoms got bigger, this attraction must get weaker. So the three things come together in explaining our ionization energy variations. So remember, down a group, we saw on the noble gases, or group 1, the ionization decreases. Well, let's see why. The nuclear attraction will get more. There are more protons down a group in each atom, but the amount of electron shielding also increases to outweigh this. Remember, the final component, the radius of the atom, is bigger as the atom gets further down a group in a bigger atom. So that means the general reason is why the ionization decreases. The outer electron is further from the nucleus. And of course, the same idea occurs, as you can see, the shielding arrangement, and the same principle. As we get more electrons, we get bigger shielding. And again, down a group, the same issue. The further out our outer electron is, then the lower the ionization. So the nuclear attraction, the electron shielding, and the radius contribute to mean that as our atoms get bigger, so ionization energy will be lower. And there's the proof. There's a graph. We've picked out the group 2 elements. And again, as you can see, there is a decrease at every level. The energy needed to remove the outermost electron, first ionization, as you can see, decreases down the group. Remember why? Because although there are more protons in the nuclei of each of these, there is also more shielding, which outweighs that because there are more full shells at each of the different positions going down a group in a periodic table. There's an extra shell of electrons. So the final issue, of course, is the radius, the size of the atoms. Well, they're getting bigger as you go down group 2. So the outer electrons are less strongly attracted and easier to remove. So that's why ionization decreases downwards. Well, of course, across a period, we have the same three issues. The nuclear attraction. The number of protons in the nucleus will increase as atomic number increases. So we've got nuclear attraction increasing as we go across, just the same. So no surprise, nuclear attraction will pull in the electrons more strongly. Now what about the shielding? Well, in the same period, remember, in the same period, you're adding electrons to the same outer shell, not an extra shell, but the same shell. So this is different. The electron shielding is constant as we go across a period on the table. It doesn't get bigger because we've got the same number of inner shells, not an extra one. So this makes a difference. There is the same shielding as we go across. So our increased nuclear attraction from the number of protons is not matched or outweighed or opposed by increased shielding. The shielding doesn't do that. The shielding is constant. So there is an increasing pull on the electrons, which is not matched by an increasing repulsion by full inner shells. And of course, our radius suffers as a consequence of this. You might be surprised to realize that across the same period, so for example, neon is actually quite a bit smaller in terms of radius than the first element, sodium, in the same period. That reduction in size is due to the increased nuclear attraction from protons, but the same shielding. So that contraction in the radius means that as you go across a period, the increase in ionization, the energy needed to remove the electron, gets, remember, although there are little ups and downs, generally it increases as we go across a period, like we showed you with the situation from lithium to neon and of course sodium to argon. So the idea of ionization explaining by using number of protons and shielding and radius gives us a good handle to explain the variations we see in the ionization energy values and patterns within the periodic table. And again, there's the proof of the periodic trend in going across a period. There is a general increase. And of course, the number of protons increases with the atomic number, but the shielding of full inner shells is the same. These all have the same full first shell only. And so there is no comparable increase in the shielding as we add the protons. So there is a shrinking, a contraction, a pulling in of the outer shell closer to the atom's nucleus. This means, of course, that the radius, the physical size, decreases. Therefore, the outer electrons are closer and therefore are more strongly attracted, and therefore more energy would be needed to remove them. So here's a little, for instance, just to sort of summarize what I've shown you. We picked out at the top there 2 elements in period 2, and we've got lithium and fluorine. The number of protons in red, 3 for lithium and 9 for protons for fluorine. So there's an increased number of protons, which would make more nuclear attraction. The number of full shells, however, is of course shell 1, just 1s, and that's constant for both. So the net effect of that, of course, is to shrink, to pull in, to contract the fluorine atom. And there's a measurement in green in picometers. That's 10 to the minus 12 meters. So it's a measurement of distance, 157 to 71. There's quite a smaller atom in fluorine than lithium. So when we put together the 3 effects, the increased protons, the constant shielding, and the increase in the decrease in the size of the radius, there will be an increase overall on the ionization energy, because the more protons and the smaller atom means that the outer electrons will be held more strongly, so ionization will of course increase. When we come to looking down a group, I've picked out lithium again, but this time with sodium in group 1. 3 protons versus 11 protons, which means another increase in number of protons, nuclear attraction. Well, number of full shells. This time, lithium has 1, but sodium, being on the row below on the periodic table, has a second full shell. So there is increased amount of shielding. The effect of that is to decrease the energy because, of course, this is opposing the nuclear attraction, and this is pushing the electron further away or repelling it from the atom. So the effect of increased protons and the effect of increased shielding will increase and decrease ionization respectively. Finally, look at the size as we go down a group. Lithium and sodium. There is clearly a bigger atom, and we get that from the extra shell that's been added. So there is a decrease in the size, a decrease in the ionization energy, because there is an increase in the size of the atom. The outer electron is further away, and so it is more easier to remove it. So we get our general increase going across a period because nuclear attraction and radius favor that with the constant shielding. Whereas down a group, we have our decrease in ionization because the increased number of protons is outweighed by the increasing shielding, leaving it down solely to the increase in size of the atom, making the outer electrons further away and easier to lose. Okay, so the final summary, it's all on this particular slide, as you can see, across the period at the top, down the group at the bottom. And again, we can see number of protons increases, shielding is constant, and radius decreases. So the overall effect is that the outer electron is increasingly strongly attracted, so ionization generally increases across the period. Similarly, but oppositely, nuclear attraction increases and electron shielding increases because there's an additional shell going down a group. So those two features more or less cancel each other out. The radius, of course, going down the group will cause a decrease in the ionization energy. So that's the fundamental explanations for our ionization properties, increase and decrease, on the basis of nuclear attraction, number of protons, the electron shielding from full inner electron shells, and the physical size, the atomic radius of the atom, and the proximity of the outer electron to the nucleus. Well, we're going to stop here because the next part, video 3, is coming up, which is successive ionization energies and what that tells us.